Hello, and welcome back to Shakespeare DaCosta. Today we're going to learn how to solve a quadratic equation. Today we're going to learn how to find a value of x that makes an equation true if that equation is quadratic in nature. In other words, if it has a term that's x squared. And you're successful at this when you have figured out how to do that, how to solve a quadratic equation using all sorts of different ways. And also, as part of this lesson, you're going to be successful if you have explored the algebraic development of something called the quadratic formula. To start off, I'd like you to pause the video here and brainstorm two different ways at least, where you can find the roots of this quadratic relation. Well, one thing that if you were unable to start, one thing that you should recognize is the roots are any value of x that makes the y value equal to 0. In other words, if we just change y to equal 0 in this equation, we're solving an equation, 3x squared plus 12x minus 36. When does that equal 0? So again, if you had not figured that out by now, please go ahead and pause the video and see if you can find out what values of x make this equation true. Well, one strategy that you could have gone, and this is sort of the easiest way to figure out the answer here, but it does require technology, and that is by graphing. If you were to graph this quadratic right here, that would create a parabola. And then you can very easily look at, hey, when does y equal 0? That's on the x-axis. And these 2 points are the values of x that make y equal 0, -6 and +2. And there you go, you're done. Another way that you could have figured this out is by remembering that, hey, if we have a quadratic, by factoring it, we can always find out two values of x that make the product 0. In other words, let's make this equal 0. Let's start to factor this side. All three of these terms are divisible by 3. So I'll factor out a 3. 3x squared divided by 3 is x squared. 12x divided by 3 is 4x. And -36 divided by 3 is -12. And then we can continue to factor this quadratic by using the sum product rule. So we're looking for two numbers whose product is 12 and whose sum is 4. And that's -2 and +6. And so this can be factored into x minus 2 times x plus 6. And of course, with that 3 remaining in front. Now, how do I make this equal to 0? Well, this is the product of 3 factors. So if any one of these 3 factors is equal to 0, then the whole product will be as well. Or to put it another way, if x was something like 2, then this factor right here would be 2 minus 2, which is 0. So we would have 3 times 0 times, actually 2 plus 6 is 8, but it doesn't even really matter that this is 8 or that this is 3. Whatever number they are, if I multiply them by 0, the product of all 3 will equal 0. And therefore, this equation will be true. Another value can be found by looking at the other factor. So -6 plus 6, that would make this equal 0. This would be -8. And 3 times -8 times 0 is also equal to 0, just as predicted. So this is maybe a second strategy to find these same two numbers, 2 and -6. But there is still yet one more. And that is by recognizing that we can take any quadratic and we can complete the square to turn it into vertex form. And then we can isolate x, because in vertex form, there is no x squared term directly. And we'll see that happen in just a moment. So here's my equation. I'm going to start to complete the square. If you need a bit more practice in this, please go ahead and pause the video now and complete the square to turn this into vertex form. Okay, so to do that, let's go through all those steps. I'm going to factor the a value, which is 3, out of the first two terms only. So that would be 3 times 3x squared divided by 3 is just x squared, and 12x divided by 3 is 4x. The -36 remains on the outside of the brackets right there, so we did not factor a 3 out of that. The next step in completing the square is to try to take this expression that's inside the brackets and turn it into a complete perfect square. So there's a term here that's missing, and that term can easily be found by taking half the b value and squaring it. So 4 divided by 2 all squared is equal to 4. And I'm going to take that number and I'm going to place it just inside the brackets right here. I'll add it and I'll subtract it. And that way I've basically added 0. Next up in the completing the square process, we're going to take the -4 and we're going to remove it from the brackets because this right here is a perfect square trinomial. To remove this from the brackets, we do have to multiply it by our a value, just 3. And so when I rewrite my equation, this -4 will have moved to the outside. And now my final step in completing the square is recognizing that this right here is a perfect square trinomial, which will factor into x plus half the b value. And these two are just numbers, which I could just collect I could just collect into one number. In other words, sort of like collecting like terms. And so my quadratic in vertex form is 3 times x plus 2 all squared. And notice this is 2 is half of 4. And then minus 48 on the outside. The reason that we turn this into vertex form, like I had mentioned a little bit earlier, is in vertex form, x is by itself. There's no x squared term to worry about. There is a square on the outside here, but because we're starting with a value of x, and if we're basically trying to retrace our steps and we can find out what that value of x is, or in other words, to get from x to 0, we took that number, we added 2. Then we squared it. Then we multiplied it by 3 and then subtracted 48. And so adding 48 will be the opposite of subtracting 48. It will undo the last step. And that will cancel it out, and we'll have to add 48 to the other side just to keep the equation true, because we can't change one side of an equation without changing the other side as well. That's not the same thing that we did here. Here, we did not change the right side of the equation at all because we added 0. And so we have not, by adding 0, you're not changing anything. Okay, so now we've got 48 equals 3 times x plus 2 squared. The last step in BEDMAS here would be multiplying by 3. So I will do the opposite of that, and I will divide all of this by 3, and that will cancel out that. And then I have to divide the other side by 3 as well, which is 16. Then the next step in BEDMAS, so I would do brackets first, and then I would do exponents. So if I'm going backwards, if I'm retracing my steps, I will undo the operation squaring something or taking the exponent of 2. And the opposite of that is taking the square root. That would cancel out the square. And then we have to do the same thing to the other side. But here is a part in math that you have to be very, very careful of. Whenever you're using algebra to remove an even exponent, you have to recognize that there is a positive and a negative answer. So you have to take the positive and the negative square root of 16. The positive square root would be positive 4, obviously. The square root of 16 is 4, and we're going to just take the positive version of that. The negative square root would just be negative 4. So the square root of 16 is 4, and then we're making it negative. This step right here is how we end up getting 2 different solutions for a single quadratic expression. There aren't always 2 solutions, but very, very many times there are. And this step right here is what creates that, or what allows that to be possible. We are not done isolating x, though. In both of these separate equations, we do have to remove the positive 2, and we can do that just by subtracting 2. And then we have to subtract 2 on the other side as well. So 4 minus 2 is 2. And over here, if we do the same thing, negative 4 minus 2 is negative 6. And what do you know? We did end up getting the exact same 2 numbers that we would have got from factored form and that we got by graphing it. So this is 3 different ways to solve a quadratic equation. To solve a quadratic equation, we can't just isolate x like we usually do with linear equations. Instead, we do have to compare the equation to 0 by making one side of the equation equal 0. As we saw, it is pretty easy to find the zeros of the resulting quadratic. Um, if you were to choose to factor it, right? If the quadratic even is factorable, then you can go ahead and do that. And then each of the factors can be made equal to 0, and then you can solve for x, and that would give you your solutions. But not every quadratic is factorable. If a quadratic isn't, one strategy that you might have, if you don't have a graphing calculator on hand, obviously, is to complete the square to turn it into vertex form, and then isolate x. So we saw how to do that. And if I asked you to find the vertex, the equation of the axis of symmetry, and the roots of y equals ax squared plus bx plus c, here we have done what's called a specific case. So in this case, a is 3, b is 12, and c is negative 36. And we were able to complete the square here, and then we were able to also isolate x to see that it was positive or negative 4 minus 2. Those are the solutions. But this question is asking you to do that without any numbers for A, B, and C, just leaving it as A, B, and C. And in that case, we call that a general case. And if we are to solve a general case, we would sort of solve this process for every single quadratic that possibly exists. So let's go ahead and start doing that. We have ax squared plus bx plus c equals 0, and this would help us find the roots. If we want to find the vertex, we know that once we have turned it into vertex form, it's really easy to pick out the vertex right there. That would be negative 2 and negative 48. And the equation of the axis of symmetry is simply x equals h. So x equals negative 2. If we were solving this generally, the first thing we would have to do to get to vertex form is to factor the a value out of the first two terms. So here, I'm going to divide both of these by a. So ax squared divided by a is just x squared. And b divided by a is just b over a. I'm just going to write it as a fraction and leave it the way it is right there. Then what we did is we took that number, we divided it by 2, and we squared it. So I'm going to do that right now. I'm going to take b over a divided by 2. And to divide a fraction by another number, I can turn that denominator into a fraction itself. And here I have b over a divided by 2 over 1. To divide two fractions, I know that I can just flip the second fraction, or I can multiply by the reciprocal of the denominator. So I'll multiply by 1 over 2 instead of 2 over 1. And to multiply two fractions, you multiply the top, you multiply the bottom. b times 1 is b, and a times 2 is 2a. And so this would be the number 4 in this case. And what did we do with that number 4? We took it and we moved it inside the brackets right over here. We added it and subtracted it. And so when I rewrite my equation, this right here is going to go inside the brackets being added and subtracted. Our next step is to take the subtracted version of it, multiply it by a. So I'll take this right here, I'll multiply it by a, and then that goes right outside the brackets right there. What's remaining in the brackets will be a perfect square trinomial. And what is outside the brackets can be combined into, this is just going to end up being a number because a, b, and c are parameters. They all represent numbers, and we can figure out what that number is right there. And if I were to actually do that, if I were to factor this, I would always end up with half of whatever this number is. So I had x squared plus 4x. That would always factor into x plus 2. 2 is half of 4. And so very similarly, I could just take this number and divide it by 2, which I'm skipping a few steps in my explanation here. But b over a divided by 2 is b over 2a. And at the same time, this all combined into one single number. I'm just going to put that in brackets. And this is actually vertex form. Here we have a. This right here is our h value. And this right here is our k value. So if I want to say where's the vertex and where's the equation of the axis of symmetry, I can very easily pull that out of here. Pause the video here and see if you can do that. What are the coordinates of the vertex, and what is the equation of the axis of symmetry once we have ax squared plus bx plus c in this form? Well, hopefully you recognize that this is x minus h. So h in this case would be negative b over 2a. And k would be this number right here, which again, I've skipped a few steps, but I'm just going to simplify it into this expression. So this is the actual coordinates of the vertex. And the axis of symmetry, the equation, is always going to be x equals h. So x equals negative b over 2a. To find the roots, now we do have to solve for x in this equation, right? What did we do here? We added the k value, or we did the opposite operation of whatever this is. So if you take a look right here, I'm going to subtract this term, whatever that term is, and then I have to do the same thing on the other side to keep the equation true. My next step in isolating x is to divide both sides by a, or divide by, in this case, it was 3. So I'll divide this side by a just to cancel that out. And then I have to divide the other side as well. Now I have to get rid of the square. And how did I do that? Well, I took the square root, and that canceled it out. And then I had to take the positive and the negative square root of the other side, leaving me with x plus b over 2a equals all of that big ugly mess that you see right there. Finally, we just had to remove the b over 2a, so I'm going to subtract that on both sides. And I found out that the value of x that makes this equal 0, or in other words, both of the roots can be found using this expression. And this is kind of an ugly expression, if you don't mind me saying, right? There's 1, 2, 3, 4 different a's, there's 2 b's, there's a square root, and there's a constant on the outside. This is a very sort of primitive version of what we know as the quadratic formula. The quadratic formula was this expression that we've created here was first created or was first sort of solved in its most general way, in the same way that we have done here, by the Indian mathematician Brahmagupta, who published it in his major work, which is called Brahmasputra Siddhanta. That was later on developed further by Simon Stevin, who was a Flemish mathematician, and then ultimately the quadratic formula was published in its final form by René Descartes, who created the Cartesian coordinate plane and is responsible for quite a bit of mathematical advancements. We're going to follow his steps and learn how to take this and simplify it now into his version. So the first thing I'm going to do is I'm going to look right over here and see if I can take this square and apply it to b over 2a. I'm going to do that just off to the side. And so b over 2a squared is simply b over 2a times b over 2a, which is b squared over 4a squared. And so I'm going to rewrite this portion right here with what it's actually equal to. Now I'm going to focus on multiplying all of this by a. So or by negative a, excuse me. So here I have negative a over 1 multiplied by b squared over 4a squared. And to do that, I just have to multiply the top and multiply the bottom. And once I do that, I recognize, hey, I've got an a in the numerator. I've got two a's in the denominator. Those will sort of cancel each other out to some degree. And what I'll be left with is just negative b squared over 4a. And that's exactly what I have here. I've replaced this expression with the one that I've simplified it to. Now I'm going to look at the entire numerator, and I'm going to distribute this negative to all the terms that are inside here. So negative 1 times c is negative c, and negative 1 times negative b squared over 4a is positive b squared over 4a. And I can even go further, and I can actually add these two together. So to do that, I do need a common denominator. So if I sort of make negative c over 1, I can then say, okay, let's multiply it now by 4a over 4a, because that's the common denominator there. Negative c times 4a is negative 4ac, and 1 times 4a is just 4a. And to add these two fractions, I keep the denominator the same, and I just add the numerators. And so I can replace this numerator entirely with this expression right here. To further simplify it, let's actually look at the fraction over a fraction. I don't like that very much at all, so I'm going to take a look at that and divide that by a over 1. So that's the numerator divided by the denominator. And of course, to divide by fractions, I could just flip the fraction and multiply it. And so 4 times a is 4a squared. And this expression here times 1 just remains the same. I'm just going to reorganize it so that the b squared is in front, so I don't have a leading coefficient being a negative, because I don't like that. And so this inside the square root just turns into turns into b squared minus 4ac all over 4a squared. Now you may or may not know this by now, but you can certainly take a square root of a product or a quotient and apply the square root separately to the two parts. So here, the square root of b squared minus 4ac over 4a squared is equal to, I could just take the square root of the top and the square root of the bottom. And then the reason I'm going to do that is because I noticed that the denominator here actually is pretty easy to take the square root of. The square root of 4 is 2, and the square root of a squared is a. And so this ends up being positive or negative b squared minus 4ac over 2a. And if I want to subtract b over 2a, well, they actually already have the same denominator. So I could just subtract their numerators. And this right here, folks, is the quadratic formula. The only change that is usually made is this negative b is moved in front. And so this right here would be the final form that maybe you have heard of before, maybe you've even seen it before. This is sort of how it was created. This is the proof behind why this can give you the zeros for any quadratic equation. So if the quadratic is factorable, one way we can solve it, or sorry, let me start over here. If you want to solve a quadratic equation, one way to do it is to make it equal to 0 and then find the zeros. And you can factor it if it's factorable. If it's not factorable, you could complete the square and isolate x, but you can also determine it without graphing, without factoring it, without completing the square, just by using the quadratic formula. To do that, you just take a, b, and c, and you plug it into this formula right here, and you evaluate the rest. The vertex of any quadratic in standard form is also easily calculated with a simple negative b over 2a being the x value, and c minus b over 4a squared being the k value, which is the maximum or the minimum. The axis of symmetry, of course, is x equals whatever the x value of the vertex is, so x equals negative b over 2a. In this example, we're going to find the zeros of this quadratic. So we can easily identify that when it's in factored form, there are any value of x that makes either of these two factors equal 0. Because if either one equals 0, then when we multiply them all together, they will be 0 as well. This is the first factor here, and it can never ever be changed because there's no x in it. Changing x doesn't change this one at all. This factor is pretty easy to take a look at. If x is positive 5, 5 minus 5 would get us 0. This one's a little bit harder. So all I have to do is make it equal 0, and then I can solve for x. So if I subtract 1 from both sides and I divide both sides by 2, I will isolate x and see that if x is negative a half, this would be 0. And then something times 0 times something is 0. If x is 5, this would be 0, and by the same token, that would make the entire equation equal to 0. And so these are the two zeros. 5 and negative a half. Solve this, verifying our solution. So here I have an equation of a quadratic, but it's not equal to 0, and I only really know how to find the zeros of a quadratic. But I can very easily fix that. I can just subtract 10 from both sides, and now I have an equivalent equation, except this one is equal to 0. Knowing that, I can very easily factor this into x minus 2 and x plus 4 by using the sum product rule, and find that my solutions are 2 and negative 4. 2 makes this factor equal 0, and negative 4 makes this one. To verify our solution, we can always check with a graph. So if I pull out a graph here, x squared plus 2x plus 2 makes this beautiful parabola. And when is that equal to 10? So here I've put the line y equals 10, and I'm looking for when does this parabola touch that line, and very clearly here we can see it happens at -4 and at 2. We can also verify our solution just by taking these numbers and putting them right back into our equation. So 2 squared plus 2 times 2 plus 2 actually gives you 10. And -4 squared plus 2 times -4 plus 2 actually also gives you 10. So there's two different ways to verify your solution. You can always check with the graph, or you can take your solutions and put them back into your original equation, and then just check to see if the left side and the right side are equal. When does 18x squared plus 29x equal -3? So this is a quadratic equation, and once again, I don't know how to solve that except if one side equals 0. And so I will add 3 to both sides, and now it actually does equal 0. And I can solve this by factoring this through decomposition, and I'm not going to go through all of those steps here. I certainly have another video on that if you'd like to check that out. But suffice it to say that this factors into 9x plus 1 times 2x plus 3 equals 0. What value of x make either of these equal 0? That's a little bit harder to figure out, so I'll just do that separately. When does 9x plus 1 equal 0? All I have to do is isolate x to find that it happens when x is -1/9. So -1/9 would make this equal 0, and I can do the same steps with 2x plus 3 equals 0, just isolating x by doing the opposite operation in the reverse order of BEDMAS to find that x equals -3/2. That would make this factor equal 0. And so these right here are our two values of x that make this side of the equation equal -3. Solve this equation. When does 2x squared minus 5 equal x? Well, again, I don't know how to solve this unless one side equals 0. So I'm just going to subtract x from both sides. And now I have a quadratic equation that's equal to 0. And I can try to solve this by factoring it. So 2 times -5, this is by decomposition, is -10. And are there two factors of -10 that add up to -1? Let's see, 1 times -10 is -10, but 1 plus -10 is -9. And so that is not going to work for me. What about 2 times -5? That also equals -10, but 2 plus -5 is -3. So that's not going to work either. And 10 actually doesn't have any more factors to test. So this quadratic is actually not factorable at all. If you're in this situation, well, then we cannot use that method where we factor it to find out when does it equal 0. Instead, we could try to use the quadratic formula. So here, in this case, I have a quadratic equation right here, ax squared plus bx plus c equals 0. And this is the expression I'm going to use. So a is 2, b is -1, and c is -5. And so I'm going to replace these values in here with these three, and I'm going to start to evaluate this. So to do that, -1 squared is +1, -4 times 2 times -5 is +40, and 2 times 2 is 4. And -1 times -1 also is +1. So I can do many steps sort of all at once. I can multiply these to get -1, I can square this, I can multiply these three together to get +40, and even the denominator to get 4. Now all I have to do is add 1 plus 40 to get 41. And this right here is actually the exact value of x that will make this equation true. And this is an irrational number, so it's very difficult. It's not possible for us to write this out as a decimal. But if we wanted to, we could say, try to evaluate the positive and the negative version, and we'd get about 1.85 and about -1.35. But these are approximate. Again, if you do want the exact value, this is the one that you're looking for. And I can just go ahead and throw that on a graph to confirm that those numbers are actually correct. Now, one thing to note when you are solving quadratics using the quadratic formula is that this expression in here, b squared minus 4ac, this is something called the discriminant. The discriminant is this expression that is underneath the square root. And because it's being square rooted, that creates an interesting sort of situation. Because not every number has a square root. Negative numbers have no square roots at all. The square root of x is not defined if x is less than 0. It creates something called a complex or imaginary number. And that's really outside of the scope of what we're studying right now. However, the number 0 does have a square root, but it only has 1. The square root of 0 is 0. Positive or negative 0 means the same thing. But if the square root, if the discriminant here is a positive number, there's always going to be two solutions, right? Negative x squared gives you x squared, and x squared gives you x squared as well. And that's the reason sort of we have this plus or minus in front. And so this idea is another thing to pull away from using the quadratic formula, that all you have to do is check the discriminant. If it's negative, there's no solutions. If it's 0, there's one solution. If it's positive, there's two solutions. When does x squared minus 15x equal negative 56.25? I'll invite you to pause the video here and see if you can solve this all by yourself. Well, here is my equation. I'm just going to make sure that one side equals 0, so I'm going to add 56.25 to both sides. And now that I've done that, I can use the quadratic formula. I have a decimal in here for my c value, so I think I was not even going to try to factor this. I'm just going to go right to the quadratic formula that's given to me right here. And I'm going to replace all of these values with what I know they're equal to be. And now I'm going to start to evaluate. So negative 15 is positive 15. Negative 15 times itself is 225. And negative 4 times 1 times 56.25 actually also is negative 225. Finally, 2 times 1 is 2. And what's going to happen here is 225 minus 225 is 0. And actually, the square root of 0 is 0. So 15 plus 0 divided by 2 is just 15 over 2, or 7.5. And 15 minus 0 over 2 gives me the same thing. So one thing to note here is, again, this is an example of when the discriminant, the number underneath the square root, when that is equal to 0, there's only going to be one solution. And if I were to graph this, you can even see that the expression x squared minus 15x plus 56.25 is only equal to 0 at this one point. That's just where the vertex touches the x-axis. Now, a few lessons ago, we talked about using a flowchart to factor quadratics. And today we talked about using the factors that we've created to actually solve the quadratic. What happens if those factors fail? Today we learned that if it's not a difference of squares, or if it is a difference of squares, we could do that. And if it's not, then we can try to use the sum product rule. If we can't, because a is not equal to 1, then we could try to see if it's a perfect square trinomial. But if it's not, then we have to use decomposition, which means asking ourselves, are there two factors of a times c that add up to b, and going from there? If there are not two factors, though, then this quadratic would be unfactorable, and to solve it, we have to use the quadratic formula. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.